Hello everyone, in this tutorial I'll be teaching you how to use the known coordinates to compute the known coordinates in Excel. So just going to open a plan, show you. So this is a plan with a known one point with the known coordinates. That's a PTN2. They're going to just move around. Then we're just going to calculate the coordinates of these outer points, mostly the corner beacons, and we're going to use Excel. So we're going to move from PTN2, and I already have the coordinates right here. And the good thing is that we have the bearing and we have the distance. So we're going to utilize the bearing distances to move from point PTN2 and to PTN3. Then PTN3 again to PTN4, like and so on. So RD2, RD6, RD5, like that. And then you will close by checking if points are correct by actually closing to PTN2. So basically, what you're going to do, you're going to use a simple technique. You're just going to calculate the change in easting and then change in northing, which is changing in easting is departure and changing in northing is altitude. So we're going to calculate them and then we add to the known coordinates. So that's how it works. And I want to show you the formula of calculating the change in or the departure and altitude. So here we have the bearing or the theta, angle theta. So if you want to calculate, now we assume this is the ground distance that you have. For example, let me open this image. Here we have the bearing 94 degrees, 14 minutes and 27 seconds. And we have the distance as 71 that's from point PTN2 to PTN3. So we have the distance of 71.27 meters. So this L represents this 71.27 meters. And the theta is the 94 degrees, 14 minutes and 27 seconds. So that's the technique that we're going to use. So we'll calculate the change in northing and add that change or altitude to our northing. Find the northing of PTN3, and also we'll calculate the departure, means the change in easting, and then add that to the easting of PTN2, and it will give you the easting of PTN3. So, and in the end, we'll have complete coordinates of point PTN3. And we're going to repeat the same process since we have the bearing distances all around. So it's as simple as that. So let's generate the formula. Now that we have L distance and we want altitude. So this is the altitude we want to move from point A to point B. And we have the L. We want to calculate the altitude. This is the altitude. It's just parallel to this one. So this is the altitude. And now we have the bearing, and we have the distance or ground distance, which is hypotenuse. So to find altitude, so let me just type something here. So altitude. Altitude is given by we have this L is hypotenuse and the altitude is our adjacent. So automatically that is cos. We'll multiply L by cos theta. So that will be L multiplied by cos, let me just type in bearing or bearing, yeah, just bearing, because I don't have the sign for theta. Likewise, if you want to calculate the departure or the change in easting, so departure which is the change in easting is equivalent to, now we have this bearing, we have the hypotenuse. What we want to calculate is departure, and if you look at this diagram, departure is actually opposite, is on the opposite side of this angle. So that's opposite and hypotenuse, and automatically if you did some trigonometry, you have this simple formula that you can just so if you have issues with remembering the formulas or the trigonometry, just memorize SOHCAHTOA, which is sine. For you to calculate the sine of an angle, you need to divide the opposite side by hypotenuse. For you to calculate the cos, for you to find the cos, you have to divide adjacent and hypotenuse. For this case, we had cos theta. Let me just theta theta. Just put it in a bracket that is equals to this formula, adjacent over hypotenuse. So our adjacent is altitude. So is altitude then you divide by hypotenuse, which is L. Now, for you to find altitude, you multiply both sides by L, which gives us altitude is equals to L multiplied by cos theta. Let me just type this one, theta, instead of bearing. Theta like that. So that's how we basically generate that formula. So let us continue for departure. Now we can see let's generate the departure. I said we have this is the opposite, this is the bearing or the angle, and we have the distance, which is hypotenuse, and we have what we want to calculate is departure. So sine theta is equivalent to opposite. This O stand for opposite, H stand for hypotenuse. So opposite is departure. then you divide that by hypotenuse, which is L. Now, for you to find the departure, you need to multiply both sides by L, so that on this side you remain with the departure. No, so departure is given by L by L multiplied by sine theta. So these are two formulas, and it is as simple as that. So the reason why I went ahead to generate these two formulas is because most people find it difficult. Most people don't understand why we multiply L by cos theta to find altitude and L by sin theta to calculate departure. So with that being said, now we have this altitude, we have the departure. We need to insert these formulas in my Excel, or I had already prepared an Excel. So this is the Excel. Let me move it, see, so that expand it like that. So alongside our diagram, now this is our diagram. So our first point is point PTN2. This PTN2 right here, PTN2. We already have the known coordinates, and I've already typed in the coordinates. It's they're just right here. These are the coordinates, and now we're moving from PTN2. We're moving to PTN3, and as you can see from this diagram, the bearing is 94 degrees, 14 minutes, 27 seconds. So there's no magic here, so don't be scared about this formatting. Let me just remove it for a second so that you can see. So these are just values that are typed in one column, and we have the degree symbol in another column, but I've just squeezed the column so that it can fit. We have column for minutes, column for minute symbol, column for second, column for second symbol. So if we can just undo that. So again, moving forward, now when we calculate, now we're going to use this point, or this bearing, and the distance to calculate the departure, and this altitude. And the altitude we said is for the change in nothing, and we said the formula is L multiplied by sine sine, then you can just type in bearing like that. Let me expand that. Sorry, this not sign, this course. For change in nothing, you said you're going to use course, and for departure, change in easting, it's L multiplied by sign bearing. Then you close that. You can just let me this bearing, not bearing, like that, and you close properly like so. And let me just wrap texts. They are properly wrapped. Just increase the length. Now that we have this type, you have this formula. So the first row, most of the data are actually empty because it's a point that we know. We don't need to calculate for it, but we have the coordinates. So these are our starting point, the starting coordinates. So the first thing you're going to do, you're going to convert this bearing. You can see the bearing is in a format that we can't use for calculation. That is it's in degrees, minutes, and seconds. So we need to convert that into degrees decimals. So in order to calculate bearing in degrees decimals, we're going to write a formula and then just write equal sign. When you want to write a formula, you start with the equal sign. Then you're going to add bearing. That's a bearing. Then plus in bracket, you're going to convert this minute into degrees. So this already 94 is already in degrees. We're going to convert this in degrees and add to that, and convert seconds to degrees and then add to that. Then we'll have bearing in decimal degrees. So since we have this we have this in degrees, then we going to convert this 14 to degrees. We're going to divide it by 60, since 1 degree makes or 60 minutes make up 1 minute, or 60 minutes make up 1 degree. Then plus in bracket this second also we're going to convert to degrees, and we know that 3600 seconds make up 1 degree. That's 60 by 60. So it's this one, second divided by 3600 seconds. You close the bracket nicely, then you just hit enter. So you then you can just format your result into two decimal places, just like that. So I'm just going to drag down, insert the remaining calculations. So if you click on that, you can see the formula has been applied to the next line. So this line, PTN2 to PTN3, PTN3 to PTN4, and so forth and so on to the last point. Now that we have bearings in decimal degrees, we're now going to apply our formulas. That is, we're going first of all to calculate the latitude, which is the change in northing, and calculate the departure, which is the change in easting. We're going to use those changes to calculate the new position on the coordinates of the respective points. So first of all, we're going to start by latitude. So change in northing or latitude, we're going to just write this formula. Latitude equals to distance L, which is ground distance, and we have ground distance is 71.27. Then you multiply that by our new bearing in decimal degrees. You multiply sine this. So again, there's something I need to tell you. We're going to convert our bearing into radian. So our formula will be like this. So distance multiplied by cos, and inside this cos, we're going to convert, we're going to write radians. We're going to convert this a bearing that is in decimal degrees into radian. So the radian function normally converts an angle from degrees to radian, and radian measures angles using the radius of a circle. And if you look at this diagram, basically what we are trying to do, this is basically a circle. So we are dealing with a circle here. So the earth is actually spherical and it's almost circle. So that's a radian, and then insert in a bearing that is in decimal degrees, that is 94.24 degrees. Then you properly close the formula, hit enter. Now let me just format this into 2 decimal places. Format numbers into 2 decimal places. Now I just going to drag this down to complete these other lines. So this, as you can see, is C9. C9 is the distance of this particular line. Multiplied by cos, we convert the bearing to radian. Simple as that. So let's move on to departure. We're going to calculate departure, and we say departure equals to sine equals to distance, and our distance is 71.27. You multiply that by sine, and then you convert to a bearing, first of all to radian, and the bearing that we want to convert to radian is this one, decimal degrees. And then you properly close your formula and hit enter. There you have your change in easting. Just double click to autocomplete for all the other lines. Now that we have change in northing and change in easting, we're going to use these ones, the latitude and departure, to calculate for the next coordinates. So what I mean is, we are at this point between 2. We have already known coordinates. Now we have calculated the change in northing, change in easting. We are going to add the change in, or rather altitude, into northing and the departure to easting to find the new coordinates, which is PTN 3. So that's what we're going to do here. So PTN 3 will be nothing, will be nothing for PTN 2. Then we add the altitude that we've just calculated, or the departure between PTN 2 and PTN 3, which is this one here, negative 2.27. So here I'm going to just input the formula equals to this one, our known nothing, plus altitude change in, or delta not nothing, that one. Then you click enter. Simple as that. So repeat the same thing for, we can just autocomplete for the remainder of. So if you just click in one of the, randomly click in one of the formulas, you can see it's M7 plus K8, M7, this one, plus K8. K8 is the change in nothing. As simple as that. You're going to repeat the same process for easting. So just write easting equals to our non-easting plus the departure. Then click enter. Then you can just double click, or you can just drag. Now we have all our coordinates. I told you we're going to check, we're going to close the loop, or to check if our calculation was correct. It's correct. So we have moved from PTN 2 all around PTN 3 to PTN 4, RD2, or that to RD1, PTN 2, and we've just gone back to PTN 2. Let's see if the PTN 2 that you have just calculated tallies with what we had in the plan. So this is the coordinates for PTN 2 that we had originally, the plan, and this one is the calculated PTN coordinates. As you can see, the original nothing was 95, or rather 984, 587, 2.4042, and easting is 244, 742.28. And what we've just calculated is 984, and you can see 984, 872, 872.42. What about the easting? The easting is 244, 244, 742, 742.29. This one is 0.28. So the accuracy, normally if you are doing a fixed boundary, the accuracy normally ranges between, the accuracy should be around 0.03, and from from our calculation. You can see that let me just subtract this one, rather this one, just type in equals to our known coordinates, nothing minus calculated one, and non-esting, you subtract calculated esting. So this negative 0.01. So this very negligible, and it's within the acceptable accuracy. So the calculation was very successful. It was perfect, and basically that's how we use the known coordinates to calculate the unknown coordinates in Excel. And you can see it's actually very easy and simple, and it is the quickest method to use. So thank you for watching. Remember to subscribe, give this video a thumbs up, and you can also share. So again, thank you for watching. See you in the next tutorial.